All right, guys, so in the last video, we just saw how anti-Markovnikov addition happens with HBr, and we use HBr a lot in our example. And the reason why is because bromine is the most favorable and the most selective to use. So HBr is better than HF and HI. HF and HI tend to be on the extremes. So, and then when it comes to HCl or HBr, Br works out better because it's more exothermic. So when we do halogenation, same thing. F2 is too exothermic, too explosive, hard to control. I2 is too endothermic. It's not, delta G is not spontaneous enough. And so we want to choose usually Cl2 or Br2. And of those two, Br2 is better because it's more selective. So the two reasons for this are, one, we're going to have bromine is going to be more spontaneous, so the delta G is more negative overall, and it's more spontaneous than chlorine. And then also it's definitely more selective because of the Hammond postulate and the idea that the intermediate is going to be more indicative of the transition state energy. And so you're going to see a bigger difference in the activation energy for these reactions based on whether you have a primary, secondary, or tertiary radical. Whereas for chlorine, the difference in those activation energies are just not as great to see a big difference in the rates. And of course, we'll just make a note here, 2 endothermic here for this reaction to occur, and this one was 2 exothermic. So I call it like the Goldilocks principle, like, you know, too hot, too cold, or just right, okay? Now for synthesis, the first reaction is great for starting with an alkane. So when you have an alkane, think back to your reaction map. You have alkanes in the corner, and there's nothing that an alkane can go to because it's so unreactive, except for one reaction that we're going to learn, and that's the halogenation reaction, which we have learned. So this reaction is the only thing you can do. So whenever you see an alkane, just know you got to halogenate it, and you can halogenate it with either Br2 or with NBS. Now remember, we like to use bromine because it's highly selective for the tertiary, so that's how we're going to control it. And if we wanted more of the, less substituted, then we should use chlorine, because at least we have more of a 50-50 mixture then, not quite 50-50, but at least definitely more of the non-tertiary one. But then from here, how do you get these products? So one's a substitution and one's an elimination. See if you can figure out what reagents you need to convert it either way. Okay, so in the first case, I've got a tertiary, so I can't really do SN2. If I use hydroxide, it's not going to do SN2, it's actually going to do E2. So I want to use a strong base to do E2. When I do that, hydroxide is small, and it will come in and grab this H and give me the double bond here. Okay, so that's E2. And then if I want to do an OH group here, I need to do substitution, but not SN2. I have to go SN1 because this is tertiary. So I'm thinking I need to let go of this bromide, make a tertiary carbocation, then have water attack it. And so all I need is water. Okay, this is a chance for us to summarize the reactions that you should know. So brominating alkanes, chlorinating alkanes. Give me an example of something you can start with, a molecule, you can make it up. Just any kind of alkane, how do you brominate it? Show me an equation for that. And then also, if you can, write out the mechanism for each one as well. Go ahead and pause it, go through each example, and then let's check our answers with each other. And then let's compare our examples with each other. All right, guys, so here are my examples. So there are lots of different reagents here, so just make sure you know, okay, when do I use Br2, when do I use NBS, when do I use HBr, okay, when do I use chlorine, when do I use peroxides, right? So there's a lot of stuff going on. And in reality, we use all kinds of reagents, things that are not even listed here, but do know there are a few times when you might see things that aren't fitting in these boxes, like for example, bromination here. Sometimes NBS is used for this, so just be aware. Sometimes, even though it's not allylic, because there's no pi bond, the only thing NBS is for bromine radicals, right? So bromine radical with an alkane, well, who cares if bromine comes from Br2 or NBS? The only thing you can do is brominate it, right? So that's what we do observe in real life. And but NBS is really especially useful for allylic bromination because the NBS actually provides bromine radical, but it's also because it's reacting with molecular bromine. So so NBS will create some HBr. When it reacts with an alkane, it takes an H away, right, from this allylic position that makes HBr, and then it also creates some Br2. The Br2 is what reacts with this ultimately. So NBS is a source of Br2 under these conditions. So that's why you can see, both of these reactions occurring with NBS. And then another question that you might think of that I didn't address in the last video is if NBS makes bromine radical and HBr makes bromine radical, then how come in this case the NBS results in a hydrogen being taken off here with the radical and it's an allylic bromination? Oops, sorry, we need the allylic position here. Sorry about that. But then in this case we have bromine radical, and how come instead of making the allylic it makes a reaction with the pi bond? So how do we know, how come it goes one way and a different way here when they both go through a bromine radical? Okay, so the answer to that is that it depends on the concentration of bromine radical. With NBS, I mentioned that bromine radical stays at low concentrations. And so because it's at low concentrations, the rate of the double bond reacting is quite low. And so when bromine radical reacts with, or when bromine reacts with this double bond, that's more reversible than when it reacts here at the allylic position. So when we have something like HBr and a lot of HBr in solution, that pi bond reacts with it a lot, okay? But if I kept that at low concentrations, then the reaction starts to compete with the abstraction of this allylic hydrogen. So as long as the concentration is low, then that becomes more significant, and that's less reversible, so you end up with more allylic bromination when that concentration of bromine radical is low. So how do we indicate that? Well, we use NBS just to assume that bromine radical is going to be much lower than if we use bromine or we use HBr. Okay. So I don't know, that's more of an advanced topic, I guess, but when you see NBS, think allylic or think regular halogenation, but when you see a double bond in HBr, then think, okay, that the addition reaction is going to dominate more. Okay, so at this point, all you have to do is just practice these and the mechanisms, okay? So maybe write them out, make yourself some problems, ask yourself what's the mechanism, or if I start with this and I have this reagent, what do I make? So some ways that you guys can practice this is to just draw out some hypothetical reactions. You could try a reaction tree. What if I have Br2 and H nu light, Cl2 and H nu light or heat, NBS, what are the different things that you would expect to make? You could also do some flashcards where on the front you have, let's say you have an alkane and you have a reagent Br2 and then question mark, and then on the back of the card you have the answer. Okay, or you might have flashcards on the mechanism, like what's the first step of this mechanism, or give an initiation step, or give a propagation step. With mechanisms though, for me, I like to just write them out on a piece of paper a few times until I can do it without my notes. So for me, that's what works best. You can also try some flashcards just for quick recall. That's what flashcards are great for. Maybe try okay, here's a reaction here. Okay, so figure out what are the reagents you need to do this transformation. So that's also really helpful. And so for this one, it would be HBr and peroxide and heat or light. Okay, so work on whatever strategies you can to practice, and of course use the problems in the book as well that are assigned as ways for you to practice this material. All right, good luck everybody.